Welcome. Today we're going to start with you donating a piece of paper to the cause. It can be a scrap paper. You will be turning it in. You will need to put your name on it. Resume the video once you have your scrap paper out ready with your name on it. On this paper, you'll be responding to the question that's on the next slide. If, in some cataclysm, all of scientific knowledge were to be destroyed, and only one sentence passed on to the next generation of creatures, what statement would contain the most scientific information in the fewest words? So you have to think about some sort of horrible catastrophe that's destroyed the life of humans on this planet as we know it. The counselors can help you through this situation. You're just imagining. And let's say whatever means was able to preserve your written word. Don't worry about the language, trying to understand English, as I would assume you're going to respond in, being understood by this next generation of creatures. Just focus more on this. What statement could contain the most scientific information in the fewest words? Spend about 4 to 5 minutes on this. Spend the first minute or two just listing some ideas of information you think would be vital for the next generation. Then spend a minute or two trying to refine that, trying to streamline into the fewest amount of words. Then take the final minute to proofread and see if you want to put forth that as the statement which would contain the most scientific information in the fewest words. So pause the video for about 4 to 5 minutes and it will continue from there. The gentleman you see pictured here is a famous physicist, and he put forth this idea that I would rather have questions that can't be answered than answers that can't be questioned. Final thing you'll jot down on the scrap paper before turning it in is, which would you rather have? Would you rather have questions that can't be answered, or would you rather have answers that can't be questioned? And the scientist who put forth this statement is Richard Feynman. So, final thing to put on your scrap paper. Would you rather have questions that can't be answered or answers that can't be questioned? Introducing you today to Richard Feynman, as he's a physicist who wrote a response to that question posed to you, if in some cataclysm all scientific knowledge were to be destroyed, as this was a topic that was discussed at a conference many years ago with some of the greatest scientific minds at the time. And in a book he wrote called 6 Easy Pieces, he discussed what he considered to be the most scientific information in the fewest words. So there's a little snippet from the 6 Easy Pieces. Here's the question that was put forth, and his short summation with the most information: everything is made of atoms. 1, 2, 3, 4, 5 words. Did I count the right? 1, 2, 3, 4, 5. 5 words. And to you and I, that's kind of a classic statement. Yeah, sure. Everything is made of atoms. There's even wonderful t-shirts of jokes, don't trust atoms. They make up everything. But this is a very profound thing to realize, that the material your desk is made of, your pencil, your paper, everything is made up of the same stuff, made up of atoms. This very much changed the way in which we viewed the world in which we live, and just a floodgate of understanding happened when we began to think about everything is made of atoms. Since we've introduced you to Feynman, I want to throw this out to you to consider throughout the study of this study guide, where he says you can know the name of a bird in all the languages of the world, but when you're finished, you'll know absolutely nothing whatever about the bird. So let's look at the bird and see what it's doing. That's what counts. I learned very early the difference between knowing the name of something and knowing something. And that's going to be key in our study guide, this particular unit, in that we'll be able to rattle off the names of things, but that's not essential. We're not interested in, oh, the atom is made up of these particles. What we're interested in is the interaction between the particles, knowing something, not just the name of something, but how these somethings interact with other things. Your penultimate study guide of your Physics A career is called Charge. We're going to look and dive in at page 2. Page 2 is where I have put a little image of the basic components of the atom, and a space over here you can jot a few notes down as necessary. Now, as I mentioned before, we're pretty lackadaisical in thinking about atoms. I mentioned never trust an atom, they make up everything. But this is something, the more time you spend thinking about it, the more profound you recognize this statement truly is, and how it just influences so much of our scientific understanding. Try and understand what I'm saying about trying to understand the profoundness of this statement. Consider the following. If we are made of atoms, then a scientist, you studying atoms, is actually a group of atoms studying themselves. Speaking of you, there are approximately that many atoms in the human body. With this study guide focusing on things that contain atoms, we're going to be using huge numbers. And then, as we look at individual atoms, we're going to be looking at numbers that are incredibly small, but we'll still have lots of zeros. So maybe the decimal place would be here and the 7 over here. And we're going to get very tired of writing and counting all these zeros. So this is going to be a perfect time where we apply what many of you in the room have worked with before, but some of you it's been a while, and that would be using your scientific notation. So on pages 16 and 17, the very last 2 pages of your study guide, we've put in this Know Your Notation. This walks you through how to work in scientific notation. This section, you'll convert each number to scientific notation, and here you'll convert each number from scientific notation. Then we're going to be calculating with scientific notation. We might be multiplying 2 numbers that are in scientific notation, and we don't want to take them from scientific notation and then do the division. We want to use this shortcut still with our math. And here we've got an example for you of addition and subtraction with scientific notation, how the multiplication is done, and how the division is done. We're going to take a few minutes, probably about 5 minutes or so, to have you get started on a couple of these, and whatever you don't finish within this 5 minutes of given time, you'll want to finish at home. So we'll set the timer for 5 minutes for you to read through how to write in scientific notation and refresh yourself on the additive, subtractive, multiplicative, and division processes. In scientific notation, this number of 7 octillion is much easier to write than 3, 6, 9, 12, 15, 18, 21, 24, 27 zeros. So scientific notation definitely going to be a very useful tool throughout this study guide. Now, as we look at the world of atoms, we have various different models of how an atom appears. We don't have an actual photograph of a single atom. I mean, just imagine the technologies we need for that, in that the dot above an I in your study guide, or a period at the end of a sentence, has about 1 billion atoms. A billion is a tremendously difficult number to try and comprehend as a human being. Especially we have game shows, win $1 million. Now ask your neighbor or think to yourself, have you lived for more than 1 million seconds? Yes, definitely. Have you lived more than 1 billion seconds? That one is no. You have to be just about over 32.5 years old to have lived for 1 billion seconds. And as I mentioned before, a dot above the eye in a study guide has about 1 billion atoms. We don't have an actual photograph of an atom. We do have images that we can render through various processes. It's similar to the way in which we capture the image of light behaving both as a wave and a particle simultaneously. So since we don't have direct photographs to go from, we have models. And these models have been developed over the years as we gain more information, many times, of course, through more advanced technology, how we're able to see how atoms interact with each other. When we strike an atom with another atom, what does this collision result in? It's kind of like a forensic scientist who arrives at a car accident. They're able to take some of those evidences and put together a situation that best fits the data for what caused the accident. So a little look at the history of your atomic model. We go back all the way to Dalton describing this kind of as the atom being a solid sphere. Thomson comes along and recognizes in 1904, so about 100 years later, that the atom is made up of positive and negative charges. Rutherford in 1911 adds to the model that we have a nucleus, a center of the atom. Bohr looks at the energy within an atom and recognizes that the electrons are at various different energy levels or specific regions. Then we have the Schrödinger model, the electron cloud model, which is the most representative model of how we understand atoms to behave today. And that is best thought of as mosquitoes traveling towards the light. You know that there's mosquitoes around there. It's very hard to narrow in and see one mosquito at one time, but you can see the whole horde of mosquitoes around that light. And these little dots are like that, those electrons at various energy levels, but it's not so much that they're locked into this orbit as they are always constantly on the move and moving from one energy level to another, but it's just a whole big electron cloud rather than these locked-in sphere rings of energy. For this particular study guide, we just want you to be able to recognize that the atom, here it's kind of more of a Bohr-like representation, contains a nucleus, as Rutherford discovered. And in that nucleus, we have what are called subatomic particles. Sub meaning below, smaller, and being smaller than the atom, we say subatomic particles. And those are protons, positively charged, and neutrons, no charge or neutrally charged. And then in that electron cloud, moving around that nucleus, we have electrons, negatively charged. So the Bohr representation, think about a nucleus, and there's electrons that are around that nucleus. Google Doodle in honor of Niels Bohr, 127th trip of his DNA going around the sun. In the world of physics, it doesn't bore you or me, with the Bohr model represented here. Something pretty interesting in the world of the discovery and understanding of atomic structure is the fact that Chadwick, who discovered the neutron, was a student of Rutherford, who discovered the proton, who was the student of Thomson, the discoverer of the electron. That's just awesome. And then, of course, our last study guide, the electron or light, photon, bundle of energy, is it particle or wave? Well, Sir Thomson is an individual who in 1906 co-discovered that electron. Here is Sir Thomson here. And then Sir Thomson over here, the son of this Sir Thomson, won the Nobel Prize in 1937, proving that the electron acted like a wave. If you remember, in 1905, Albert Einstein won a Nobel Prize for his discussion of light as a particle, the photoelectric effect. So there's this wonderful evolution of understanding and improving upon information as we go through our atomic modeling. To try and help you understand just how small the atom is, picture, if you will, a speck of dust. very happy image, and you recognizing a speck of dust is really mostly comprised of dead human skin. So a speck of dust on a scale where an atom is the smallest thing on our continuum and the Earth is the largest thing on our continuum of comparison, speck of dust would be halfway in between. So size relative, if we were to sort these, atom, Earth, dust, a speck of dust, the atom, the smallest thing, the Earth, the largest thing, a speck of dust right smack in between is the middle of size between these two. Maybe this will help comprehend the size, smallness of an atom. If a nickel were as big as the Earth, an atom will be the size of a nickel. If a nickel were as big as the Earth, an atom would be the size of a nickel. If you were to remove all of the empty space from the atoms that make up every human on Earth, the 7.5 billion of us, the entire world population could fit into an apple. And if those haven't made you go, enough, here's one more. There are more atoms in a glass of water than glasses of water in all the oceans on Earth. Definitely things that make you go, There are more atoms in a glass of water than there are glasses of water in all the oceans on Earth. What if an atom's nucleus were enlarged to the size of this letter O? Now this would be a letter O in print on your study guide, not necessarily on your screen here. If so, an atom centered on the pitcher's mound for baseball would reach to the warning track. So if the atom nucleus is centered on the mound, the electron would just be about the standard warning track in most ballparks for their home run. Which is why this is fascinating on your study guide front cover. If the proton and neutrons in this picture were 10 centimeters across, so 1 decimeter, then the quarks and electrons, so quarks are subatomic particles, then the electrons and quarks would be less than 1/10 of a millimeter. So that little tiny space in between your thumb and forefinger when you make your crunchy face looking at that up at the light, break that into 10 even pieces, and 1/10 of those pieces would be the size of the electron, and the entire atom would be about 10 kilometers across. 10 kilometers across. Hence, atoms consist of mostly empty space, which means the computer you're looking at, the screen you're looking at, the chair you're sitting on, and you yourself are mostly not there. If you were to take a human and move all their electrons right up against their nucleus of their atom, we would take a human and pretty much reduce them to the size of about a flea.